All right, so this is 126, and we're down to kernel debugging. There's not much left of this course, just a few more. And there was going to be a guest speaker, but I didn't have one, so I'm just going to talk about Rust, demonstrate the Rust projects here. Rust is interesting, and I've got some projects ready to go, so you can see the joy of Rust, which I think logically belongs in this class. So let's talk about kernel debugging. We've already done debugging with WinDbg, and here's the book chapter to talk about that. So let me make sure I'm recording. I lost the recording last time. Okay, today I'm recording correctly. All right, so WinDbg we've been using. WinDbg is really old, but it's really popular because it's easy to use. It makes it easy to step through something and put in breakpoints and everything. And if you go from WinDbg to Immunity, Immunity is based on the WinDbg code, and it adds some command line features and extensions you can put in. And then there's x64 debug, which is the Windows graphical debugger that's probably even more modern and open source, but none of them can do kernel mode debugging. They're all userland only. For kernel mode debugging, the only debugger available is WinDbg, and the experts use WinDbg for everything. You can do userland debugging with WinDbg, but it's a lot less user-friendly. So, kernel debugging, you must use WinDbg. I'm not aware of anything else that can do it. I suppose there might be something, but WinDbg is what everybody uses. It's the official Microsoft product to debug the Microsoft operating system, so it seems like it'd be very strange to use anything else. So, device drivers are the main thing you're going to see in the kernel. If you have any hardware, like a printer or a sound card or anything, it's got to have a driver, and that comes from the person that manufactured the hardware, and it takes the electric signals from the Microsoft operating system and turns them into the signals to control the device. So the drivers load into memory and stay resident and run in the kernel. The kernel is the part of the operating system that must be in RAM all the time your machine is running. It's not very big, and it lives in RAM, and all your API calls ultimately go to the kernel. So applications do not directly access the kernel drivers. Here you get some of Microsoft's baffling terminology. The kernel drivers is a hardware driver in the kernel. The object that you connect to in software is called a device, which the device is not the piece of hardware. The device is a computer object, a C++ object in userland. So that's what Microsoft calls it. A device object is the userland object that your program connects to. So as typical, like I say, I mentioned the way to remember Microsoft terminology is everything is the opposite of what the name says. So a device is not a piece of hardware. It's a software thing. A driver creates a device. Install the driver, it creates a device, which is like the handle you use to refer to the driver from userland, and ultimately, therefore, to send signals that will go to the hardware. So if you have a USB flash drive and you plug it in, your operating system will hunt and see if it has a driver for it. And Windows today has many drivers pre-installed, so usually you do not need to install a driver. It's already got the driver. So it finds the driver, and then the driver in the kernel creates the device object, which gives it a drive letter. And that's the object. Now you can read and write to drive F, which is the device that goes to the driver that goes to the hard drive. If you plug in a second flash drive, and it's the same brand, it will use the same driver and create a second device with a different drive letter. All right. Now remember how DILs work. DILs are in userland, they're not in the kernel, and when you load a program, when it loads, it looks in the header and says, oh, I need this library, WS232, and then it connects to that. It looks in the export table, so DIL loads. The export table lists the functions it offers, and when you first load it, it calls DIL main, which prepares it for use. The DIL main is the entry point just to prepare it for use, and then all the other things it's exporting can be used as functions to execute the functions in the library. Drivers are similar, but different. DILs are what you use to add extra code to a program in userland, and drivers are what you use to load extra code in kernel land. So they're loaded into the kernel, and when they're first loaded, the driver entry procedure is called, which is the analogous thing to DIL main. That prepares the driver for use, and it prepares callback objects, which are like the exports, which are what's used to create those devices that connect to it. So it tells you here how to define a callback object, and here's the sort of API calls you'll see for that. Initialize object attributes, create callback, notify callback, registered callback. These are some of the API calls that are used in this process of creating the callback object to connect to the driver in the kernel. So DILs load into memory when a process is launched and run in userland. They execute dill main, and then they have an export table. Drivers loading the kernel when you add hardware. They execute driver entry and prepare callback functions and callback objects. That's the comparison of the two. So dills expose functionality through the export table, but drivers don't. Drivers register the address for callback functions, and they'll be called when a user space component requests a service. So driver entry performs the registration. Windows creates a driver object, and that then creates a device that can be accessed from user land. So here's a normal read request. If I want to read a file off a drive, then user mode application obtains a file handle for the device. You do fopen, and you get a handle. Then you call read file on that handle. The kernel processes the read file request. It then passes it through the callback function to get to the kernel object, and that will get to the real physical hard drive, or SSD, of course, these days. Mostly what malware does is it uses device I/O control. This is a low-level module that you can use for multiple purposes, and this is like we talked about before. A malware will often just use // the root of the whole system to refer directly to hardware without going through the normal process, just because it will then surprise your antivirus and other analysis tools. So this is one way to go directly to a device managed by a driver, passing in an arbitrary length buffer and receiving an arbitrary length buffer of output. This is analogous to raw sockets, where you just make a raw connection to a network socket instead of going through any higher level that would do the normal thing for you, like read a file or download a file. This just lets you send some data and receive some data from an object in a generic way. So normally what you do is go through kernel 32, then to ntdill, then to ntosdill, and then you contact drivers in here. You could have a malicious driver, though, in here, and then you can have a driver mode, kernel mode rootkit with this sort of thing down here. All right, so kernels, there is some malware that lives entirely in the kernel and has no user land component. And I don't know how common these are anymore. The Microsoft defense in the kernels I mentioned have gotten very good. That's why I don't have any projects anymore with kernel mode rootkits. It used to be possible back around the days of Windows XP and maybe Vista to do this. The defenses are getting really strong, and it's hard to do anymore. I think they still do exist, but they're too complicated for me to understand and write projects about so far. So NTOS kernel, the drivers usually don't actually connect to any hardware. They interact with NTOS kernel and hal.dill. Hal is hardware extraction layer, and it's another like a driver running in the kernel. This has the code for the OS functions, and this has code for interacting with the main hardware components, like the motherboard and the processor. And malware will import functions from these so it can manipulate the kernel. So it's usually, of course, not tied to any real hardware, but it's pretending to be a driver living in the kernel in order to manipulate other processes. And then it can hijack kernel calls and make them lie. So when you try to read the file system, you don't find all the files and that sort of thing, all the good stuff rootkits do. All right, so let's try a Kahoot. That is chapter 10, I think. Yeah, chapter 10. All right. This is 126.10a. All right. King Musk, that's right. He's like an infant terrible, very, very much like Trump. It makes a lot of sense that he's now a Republican on Trump's side. He always should have been. I mean, he's totally the same kind of guy. I think he says he supports DeSantis, not Trump. All right. All right, so what is it applications directly interact with? Yep, they interact with the device object, which is a software object in user land. All right, so what code is loaded into a process? They're DILs. Drivers are not loaded into a process. DILs are in user land. The processes are in user land. And the libraries are what loads into them. Dynamic link libraries. When a driver is loaded, what procedure is first called? Yep, that's driver entry. When DILs are loaded, they call DIL main. When C programs start, they go to main. When C++ programs start, they typically go to _start. That's where I see them go. Anyway, but it's driver entry for drivers. All right, so which of these runs in user mode? Yeah, this one, you just have to remember the Microsoft adage, the one named kernel is the one that is not in the kernel. Just the way you remember everything in Microsoft world. All the rest of those are in the kernel, but the one named kernel is the one that's not in the kernel. All right. Ghosts. A little bit late. Warning. That's good. I know who that is. All right. Good. So, let's go on here. So, all right. So kernel debugging. All right. You can do it in a virtual machine. Now, we've talked about ways you can do single machine debugging, but you don't get full debugging features that way. To really get full debugging features like breakpoints, you need two machines connected together. Now, you can do it with two virtual machines, and years ago I used to have my students doing this. It's very painful in VMware. In the old system, you had to have a serial port connecting them, an old 25-pin serial port which no longer exists. You can supposedly make a virtual serial port in VM, but it really didn't work very well. The students had great suffering. But in principle, you could do it. Now, the book talks about using boot.ini because your book is really old and it's talking about Windows XP. Windows XP had a text file called boot.ini, and you could edit that to turn on kernel mode debugging. But ever since Vista, we now use bcdedit, and you use the bcdedit/debug on to turn on kernel mode debugging. And then you install the debugging tools from Windows, which the only thing you need is WinDbg. There's a lot of other tools, but WinDbg is what you need. And then install WinDbg. There's a opportunity to install all kinds of junk, but all you want is the debugging tools. And then if you want to do it with a single machine all alone, you run livekd, and we've talked about this before. So you run livekd -w, and it will then ask you about loading symbols, which we'll talk more about later, and then it'll launch WinDbg and let you examine your current running kernel by tricking WinDbg into thinking it's a crash dump. So you can examine it. You can't put breakpoints in or stop it or anything, or modify it, but you can examine it, which is pretty good for being able to use only one machine. And so then it will load, and now you have commands you can execute here to look at it with WinDbg. So there's these command line commands which you've already used in some of the projects. So dx reads from memory, and the x is you don't type in x, you choose A, U, or D. DA will read ASCII text, DU will read Unicode text, And DD will display 32-bit double words in hexadecimal. So DA would show you the ASCII text starting at that location. And there's also DB, which will display in both ASCII and text. Then you can edit memory. Of course, you cannot do this with only one machine. This is when you have two machines connected and you're going to modify memory. Then you can edit ASCII Unicode or just write hexadecimal code. And you can use arithmetic operators. So you can do DWO, reveals the value at a 30 location pointer. So this is resolving an indirect address. So DWO will show the first argument for a function. It will go to the address ESP plus 4, which is where the first argument for a function is going to be when you're calling a function, and then it will display it in Unicode. So if you had a string argument being passed to a function like file open, this command would show you the value of that string argument. And this is what's done for you automatically in Ollie. You have the stack, and it just shows you right next to the address what it points to and the string. It doesn't do that automatically in WinDbg. You have to learn these commands to see what string is being pointed to. You can set breakpoints, the usual thing. You can specify what action to take. So you can have little scripts right here in the command line. This will set a breakpoint at get process address, and every time get process address is executed, it will dump ASCII, the object, the second argument, at 8 bytes down from the stack pointer, and then continue. So what this will do is it will let you could put this on this get process address, and then it will print the name of everything that's open, every process that's open. This is the little script you can put in the command line, and then you just reveal, like a print statement in your kernel, what's going on. Or in this is in a Windows API call in userland, but it's the same. You can do it the same thing in the kernel. This is the kind of thing you learn to do if you get good at WinDbg. That makes it very powerful. And so instead of having these automatic things like Ollie, where it shows you what you need, you learn how to write scripts to get whatever you need. And it can be little one-line scripts like this, but you can also write more complicated ones. Like say LiveKD only lets you examine things, but you can do all those, you can still have those scripts and everything. All right, LM lists all the modules. It'll give you all the exes and dills if you're in user space, and if you're in kernel mode, you'll get all the kernel drivers. And that's as close as you get to a memory map. I was unable to find a Ollie debug type memory map of the kernel. I think it doesn't exist. The kernel memory management is extremely primitive, and that's why you can crash the kernel with a blue screen of death if you make any process use up too much memory, which is really rude. So LMM disk will, let's get rid of this. Oh, maybe I'll let it go. All right. Well, if I've already bought it, but I don't know if I have the key on this thing. Anyway, so LMM will load the disk driver. That'll load the disk modules containing the word disk. And on this machine, it found the disk driver. See Windows disk, and then along, this looks like a GUID. Not very informative, but anyway, that's one way to see the disk driver. So DDNT will show the start of module NT, and this will show the first 10 words in hex of the NT, and NT is NTOS kernel. And we'll do all this later in the demo live. All right, so that's DTNT. This is the start of NTOS kernel, and I think this is the MZ that starts every Windows executable. And then somewhere down here, this is going to be the text, this thing cannot be started in MS-DOS mode or something like that, because it's an executable like anything else. And here's the first 10 bytes. 10 means 16 32-bit words. So it's 4 rows with 4 32-bit words in each row. And HH gives you the Windows 3.1 chum file help, which is what you need to learn WinDbg. Everything is in here. This is where you learn it all. This is far more valuable than any web page I found. This is where you go to learn how to use these commands. And there's no very logic, it's not much logic or pattern to the parameters. You really have to just learn them. It's a strange alien language. And so R, for example, will dump registers and so on. I found a web page too, that's another way to go, but I think just going right to the chum file is probably the best way to learn WinDbg. All right, so let's try another Kahoot, which will be 12610B. Lua is a language I've never used. Wireshark scripts are in Lua. I've never learned how to write it or even looked at it yet. There are so many languages. R is another one. It's pretty hot these days, and I haven't learned that one either. Anyway, but at least we'll talk about Rust in a couple of weeks. But there are so many languages. All right, so which command will set a breakpoint in WinDbg, of course? EP, that's kind of logical. All right. Which one will show memory as ASCII? Dump ASCII, DA, that's good. All right, which one will show you the kernel drivers? LM shows you the kernel drivers if you're examining the kernel with WinDbg. If you're in userland, it will show you the processes and DILs. All right, which one will change memory contents? E will edit, ED will edit a double word, a 32-bit hexadecimal value. All right. Same people as last time. All right. So let's go back to here. Good, we got time to keep going. All right, so then she talked about symbols. The symbols are these PDB files. When you compile code in C or C# or there's usually some C derivative used here, you can choose whether to include symbols or not. By default, the GCC compiler and most of them will not include symbols because you normally want your code to be small and you also want to make it hard for reverse engineers to examine it. Only by turning on a debugging option do you include symbols, just so you'll be able to more easily debug the code, and you don't do that for production code, but just for code during development. So if you include symbols, then instead of having to refer to hexadecimal addresses, you can refer to the name of that location for all these named locations and drivers and functions and stuff. Microsoft does provide symbols for quite a lot of the objects in the kernel. Then you can use the name and symbol name. So the module name is the name of the executable DIL or sys file without the extension. And then you have an exclamation point and then the name of the symbol after that. The exception, however, is NTOS kernel. Since you refer to it all the time because that is the kernel, it has a short name, NT. NT stands for this NTOS kernel.exe. So NTbang, NT create process, will refer to that named function, and you will unassemble it. So you'll see the disassemble of that function. So you can do NTbang create process. I'm not going to do the live demo now, we'll do it later. And then you'll see the first few bytes of this, and you see, as always, these are the raw bytes, and the instructions vary in their size, and here you see the assembly code. And so you can do create process, it'll do some default number of bytes, or you can say you can control the number of bytes with an L here. You can set a breakpoint, unconditional, I think that is, and then you have the module exported function. This will set a breakpoint on this exported function as soon as this module is loaded. So it'll wait until that module is loaded and then break when it calls that function. IMENT is a function that finds the entry point of a module, which is nice. So if you do this, then it will break on the entry point of the driver before any of the code runs. As soon as that driver is loaded, it will break, and then you could do something like print out probably as a parameter and or whatever you want to. So this would be what you're doing if you're having a problem with the device driver. You'd set a breakpoint, so as soon as it uses the driver, stop, and then you can step through it and find your bug. That's the idea. You can search for things with X, so XT, NT, you can give it star, create process star, and it will find all these functions that contain the phrase create process in the name somewhere. And this, of course, relies upon having the symbols, and the symbols for NT are always appearing in WinDbg. Other processes may not have the symbols, but you always get the symbols for NT. So you can find the closest symbol with ln. This is handy. You can do ln to find the closest match. So if I do ln at this address, it will find the closest thing is right there, this name of this, and there's another one after it. So if you have a reason to believe that a function starts near this address, you can just list and find the named objects near that address and give you some idea what's going on. You can view structure information with DT. This will give you type information about structures. And so this would be the same thing, module name, bang, symbol name, or an address. And then if you refer to just this, you'll get the structure of the object. And if you add an address, it will take the data at that address and load it into the object. And I think I got an example of that. Yeah, here you go. This is what you get if you look for driver object. You get the generic description of the C++ data structure for a driver object, which is, a 2-byte, an integer, 2 bytes here for type and then size, then a pointer to a device object, then down here a Unicode string for the name, and so on. This is just a C++ data structure. And if you then put an address in there, then it will fill in the data. And I might have one of them. Yeah, I do. So now you give it DT, NT, bang driver object, and then the address of the beep driver. And now it will give you this and fill in the values for beep. So the name of this thing is driver beep. That's the thing that is supposed to print beep when you hit Control-G. At least it did in the days of MS-DOS. I don't know if beep actually works anymore, but it's still in the kernel left over from MS-DOS. It used to go beep when you hit Control-G. I remember doing that like 30 years ago. Anyway, the code is still in there for whatever reason. All right, so driver init is called, and it was back here. You could see that driver init is here. That's part of the data structure. It defines the driver init address as part of the driver, so it will launch that code as soon as the driver is loaded. All right, and therefore, if you were to make malware with a tool like Metasploit, which we've done, it just puts the whole executable malware right there. So when it loads, it runs it right away. That's one way to do it. Then you don't have to bother calling a function. You just load the driver, bam, and it goes. I know that's how Metasploit makes malicious dills, and I don't know if Metasploit will make malicious drivers, but if it did, it would probably do the same thing. That way you don't have to bother writing any more code. You just need to load that driver. So, if your debugging machine is connected to an always-on broadband link, you can configure WinDbg to always automatically download symbols from Microsoft, and it will cache them locally. The symbol files are kind of big, and this stuff all dates from a really long time ago, WinDbg, when you have slow, unreliable network connections. That's why it doesn't include all the symbols by default. You have to get the symbols for exactly the version of the modules you have. So it has to be tied into the Microsoft servers to get exactly the update level of your system. And you can download the packages offline and store them locally if you want to, or you can configure WinDbg to automatically download symbols. And that makes it take longer to load, but then you have symbols for all the modules. All right. So let's do 10C, which is here. Haven't found the right combination of close. Anyway. Pretty good. Cats. Today on our podcast, Caitlin showed she got a feral cat a week ago. And now that cat will sit in her lap and let her pet it. In 1 week. I didn't think that was possible. I thought that would take years and maybe never happen. She's the cat whisperer. Anyway, That's what she said. She said, you feed it good food and it'll love you. I thought it would take a lot longer to civilize a cat, but apparently not. Apparently not in her case. All right, which one will set a breakpoint? Okay. It's not a duplicate of this one. So this one will set a breakpoint at the start of fast-fat. And I think fast-fat must be to read a fat volume like a thumb drive. I'm only guessing. You have to look up and see what it does. Anyway. All right, what command shows the type information for structure? Yep, this gives you the C++ data structure of that structure, driver object in this case. All right, which one will list all the functions in the kernel? All right, this is it. Examine NT all symbols. I'll give you all the symbols in the kernel, which will include all the functions. I think it will include other things besides functions too. So the only thing I ever use it for is functions. All right, new winners today. This one. And another repeat winner. Good. All right. So I think we can keep going. All right. So in practice, here's a program that writes to files from kernel space. Now that is a difficult thing to do. It's something that a kernel mode rootkit might do. You're not supposed to write to files from the kernel. You're supposed to do that from user land. Kernel mode programs cannot call user mode functions like create and write file. They have to use nt create file and nt write file, the kernel functions which these in fact go to. So the user space code here would create a service with the create service, and here it is pushing a bunch of parameters on the stack. So things like the binary path name and the desired access and the service name and so on. This is going to create a service. That's what user space code looks like. It's a load a kernel driver. And here you get a handle to a device object. So you're just pushing a bunch of parameters on the stack again, like flags and the share mode and the file name, and then you call create file. And it creates that file and returns in EAX a handle to the object, which you'll then use later. That's EDI. It's got to be set to this path. I mentioned this before. This is the low-level path to refer to an object by the root of the entire operating system. Backslash, backslash, dot, backslash. So once malware has a handle to the device, it'll use device I/O control, which we said before is the low-level way to handle a device. So it's going to call device I/O control, and again, you just have a bunch of pushes to put things on put parameters in. And here you have things like the handle to the device and the I/O control code and an in buffer and an out buffer. So you can send data in and get data back. So in kernel mode code, you can do this, but only if you have two machines together. It doesn't work with live KD. You see every kernel module loads. And so you'll see one module that loads all the time is file writer loading all the time. Normally, you wouldn't see anything loading unless the hardware is changing. So you shouldn't be seeing things loading and unloading, although you will see kmixer.sys. This is something that VMware does. That's an artifact of VMware. So don't worry about that. So, all right. So drive object will show a driver object. So here's looking for file writer, and it's going to load symbols for it, but it couldn't find the symbols, which is reasonable because it's not an official Microsoft driver that's going to have a symbol in the Microsoft website. So it's going to find it here. There is a thing called filedriver.sys, and it will show you where it is found. And so you can use DT to see the structure of it, And so it's a driver object, and here's the structure. So its Unicode string is driver file writer, and so on. So now you have a kernel mode structure that will write to a file, and it'll eventually create this file, DOS services C secret file. So this is called a fully qualified object name. We normally only use this part, C:\secret file, but if you refer to it from the root of the whole system, you give it the root object, which is DOS devices, which will get to hard drive or storage. So applications work with devices, not drivers. So if you want to find driver object, you look at the user space application to find the device object. Then you use it in user mode to find the driver object, which is in kernel mode, and you use dev object to find out more about the device object, and dev handles to find applications that use that driver. You see who has handles to it right now, so you know who's using it. All right, and so then we get to rootkits. Rootkits alter the functionality of the fundamental operating system, so system calls like to list all the files on the drive no longer work the same way, and therefore you can hide processes, network connections, and anything else from the antivirus and all the other processes, which is the point of rootkits, is to modify machines so you have remote control, and so people cannot detect your remote control and remove it. Most of them modified the kernel, at least up through maybe Windows Vista. I don't know which was more popular now, but the main popular method was the SSDT hooking. And I used to have projects in here where you'd actually do this, but modern versions of Windows won't let me do it anymore. So SSDT is the System Service Descriptor Table, and it is a lookup table of addresses to kernel modules. So this is the easy way to do it. Now when you do a syscall or sysenter or an int2e, these are ways to enter the kernel, then you jump into the SSDT. So sysenter is what you use these days. You put in your function code, and then it calls the kernel, and it goes to this table. So here's the code to create a file. You put 25H, which is the code for NT create file. Then you put a pointer, I think, to the name here, and you fill the parameters in these, and then you do sysenter. Sysenter is the call of the kernel, and it's going to use the registers as the information for their arguments. That's how it works. You load registers, and the EAX register is the one that says which kernel call you're making. And then, depending on which one you're making, other registers will have the parameters, like the name of the file and such. So here's the SSDT. The SSDT is just sitting here with a bunch of entries, and each one of them just points to NT functions. That's what's going on. And the reason you have to have this is you might have put on a Windows update that changes these kernel functions, and yet your compiled software like Microsoft Word will not change. So it's going to try and call create file, but create file might have moved. So your Microsoft update will change the create file function, and it will change the SSDT entry to point to where it is now. That's why it has to be there. So that's the point. So all you do in a rootkit is you change this number in the kernel, and now every time somebody tries to create a file, they call your malicious function instead, which modifies what create file does. That's called SSDT hooking, and this was used not only by rootkits, but also by antivirus products and firewalls. Everybody got into messing with the kernel, which is why product would have blue screen of death, and Microsoft got increasingly irritated by this, and that's why they made more and more efforts to lock everybody out of the kernel. So everybody would stop messing with the kernel. So you can hook it. So the rootkit will now call the original NT create file and then remove files it wants to hide. That's one way you can do it. So, of course, most of the hooks do reproduce the normal function because they want it to work most of the time the normal way. Otherwise, the computer would be broken. They just want to change it a little bit. All right. And however, dir does not use NT create file. So if you want to stop people from seeing the extra files you're adding with dir, you have to hook other functions as well. So if you want to detect these kind of rootkit, it was pretty easy, and I had hands-on projects for this years ago, but I took them out because they're kind of out of date. You just look for unreasonable values in the SSDT, which is surprisingly easy. I think I got it. Yeah, here's what I did. So you look down here, the kernel is at address 82, and it's not very big, so everything starts with 82, the unmodified kernel. And if you had a rootkit or a old firewall or antivirus installed, it will modify it, and you'll see it's 80, 80, 80, and one of them is just totally different, 1F. So it's really easy to detect SSDT hooking. All right, and so you can find the malicious driver. LM will list open modules. They're all going to be drivers in the kernel. And see, this one's named rootkit. That's pretty obvious. They probably have a more sneaky name than that, but anyway. All right, so you can list the rootkit function. You can disassemble the code, and you'll see it's going to call ntCreateFile. So this is the Trojan ntCreateFile. So it's going to do some extra stuff and then jump to ntCreateFile. And up here, it's going to do something like compare it to some list of files not to show you, and only call the create file if you're not trying to modify the files it's protecting, that sort of thing. So you got interrupts. Interrupts allow hardware to demand immediate access, like somebody is pressing a key on the keyboard, something's coming in the network. So you have IO connect interrupt to register a handler for an interrupt routine. That'll have an interrupt service routine, and there's an interrupt descriptor table, like the SSGT, which specifies as the interrupts come in, what should I do when an interrupt happens? And you can see them in the kernel too. So here's a sample IDT showing various things, spurious service, whatever that is, reboot is come with an interrupt, and various other things, like mouse, somebody's moving the mouse, that sort of thing. Any kind of hardware will generate an interrupt saying, stop whatever you're doing and pay attention, I'm moving the mouse, therefore you should move this arrow on the screen, and things like that. So you can load a driver to test it. There's a thing called the OSR driver loader tool to use for that. And so here's kernel issues for later versions of Windows. The main thing I mentioned before, BCD edit, no longer boot.ini. x64 versions, and almost everything is now 64, they have patch guard, so third-party code cannot modify the kernel, including the SSDT and the IDT. That's why I took those hands-on projects out, because you can't really do it anymore. And like I say, that's why, as far as I know, kernel mode rootkits have gotten much more complicated. Anyway, there are 64-bit kernel debugging tools. All right. And so driver signing is another one. All 64-bit versions of Windows require all drivers to be signed by Microsoft. You have to submit them and get approval, because unsigned, buggy drivers caused all these blue screens of death. And Microsoft is irritated by other people's code breaking the OS. So it'll only digitally signed drivers. You can turn it off with a BCD edit command, but you normally don't, and you just use proper signed drivers. That's how you can specify no integrity checks if you really want to run crappy old hardware, like if you are installing a server operating system or a 64-bit operating system on some machine with like a really cheap old NIC with a lousy driver. You can modify Windows to run in a mode and use your lousy driver, but of course they don't recommend it, and it might cause the blue screen of death. All right, so let's take a look at the last Kahoot, which is here. Getting a lot of people with goofy names. Turkey and a laser or something? Oh, dinner. Oh, dish, yeah, dish and fork and spoon, like a knife. And this is see no evil, hear no evil. Is it pretty cool? Yeah. Speak no evil. That's right. That's it. Yeah. Okay. Cool. This makes a statement. All right, so which module is loaded and unloaded all the time by virtual machines? All right, K-mixer. All right. And what's the normal function that you use to execute kernel code? Sysenter is the modern way to do it. int2e was the really old way. Sysenter is the modern assembly language instruction to call a kernel module. All right, what is the object rootkits modified? Of course, the older kind that I've talked about in this lecture. SSDT, and I sort of feel bad I'm talking about this old technique. The new technique, there is a whole book called Rootkits, written by the guy that wrote them for the NSA, and it is mind-boggling. If I ever understand that book enough, I can add more to this course, but they've gone beyond this, and there's some new technique which I don't know, but it used to be SSDT hooking. All right. All right, which one of these does Windows 10 not use? All right, boot not any. All right, if you want to use unsigned drivers, what do you use? Yep, no integrity checks is the boot flag to let you do that. All right. All right. Went all 4 times. Good for S squared. All right. So I'm going to stop the recording.